All right, so to get started, I have just two sketches for you guys to make. We've been sketching a lot, so there's not a ton of transformations on each one here. There's really just one on each. I want you guys to graph f of x equals negative sine x, and in the dashed line here, we've got the basic sine function sine x, and then also I want you guys to graph the cosine of x plus 90 degrees, and I'll let you guys do that while I do attendance. All right, I'm going to play catch up with the first one. So essentially, it's just the sine function, but just reflected. But for completeness sake, I will fill out my table. No phase shift. We'll have the classic period of 360 degrees, amplitude of 1. But yeah, it'll just be our sine function, but we just go down first instead of going up from 0, 0. Fill up my graph with points. Smooth curve, not too bad. I'll give you guys another moment to graph the cosine function. If you're at home, you can just pause the video and make sure to give that a try yourself. Recording, and let's see what you guys had for the cosine function. I'm just joking. I don't monetize these videos. No desire to. Okay, so what do we got? We got our axis. Nothing's changed. Phase shift, left 90. Nothing changes the period. Nothing's changing the amplitude. So it's our basic sine function, but our cosine function, but our first maximum where we start is just left 90. And then period's 360. Halfway in between those, we get a minimum. And then halfway in between max and mins, we come back to the axis. So now that we've done both of those, people at home can pause the recording and just think on this for a second. What did you notice about the two graphs? Take them both in. What'd you guys notice? Paige, what'd you notice? They're the exact same graph, right? Now, this isn't at this point in the unit, that's not a shock. You guys have seen that sometimes two different looking equations can make the same graphs. Let's jot that down. Paige noticed they are the same graph. But today we're going to draw kind of an interesting conclusion. What you guys and what we have just shown there is that if you take the cosine of any angle and you add 90 degrees to it, that is the exact same as if you took the negative of the sine of that angle. That's exactly what we just showed by sketching those two graphs. They had the same graphs. Now, I have some space to the side here, and let's just verify that that's true. Can somebody just give me just a random number? 24. All right. The cosine of 24 plus 90, that is 114 degrees. Can you guys just humor me and do the cosine of 114 degrees on your calculator? Of course, I'm fully prepared and have my calculator. Yes, I do have one. The cosine of 114, whatever that is, to a few decimal places, it's negative, which doesn't surprise us. Negative 0.4067. About. Did you guys get that too? Now, if you do the sine of 114 degrees, give that a go. see what, excuse me, sine of 24 degrees. That was our favorite number. Sine of 24 degrees. Please work, please work, please work. Yeah, of course it worked. I know what I'm doing up here. You got the same number. It was just negative, right? It was the negative of negative 0.4067. It was the opposite sign. This would work for whatever value you plugged in for x. The graph showed these two things are equal. We just kind of verified it works for a random number. We could try more and more and more, but you're going to get the same decimal all the time. So what we just saw, these trigonometric ratios, cosine x plus 90 and negative sine x, that statement is always true. It doesn't matter what the angle is. This kind of statement, we're giving this a new name. This is an identity. And so today we're looking at trigonometric identities. We're going to learn, this is the point in your math careers where they're introduced. In grade 11, there's 3 basic ones you learn, and then you use those to prove some more complex ones. And then grade 12, you learn a few more, so that when you get to calculus, you can do all the calculus things. So let's jot down kind of a formal definition of an identity. I'm going to type this one out. Size 20 should be good. All right, identities. An identity is an equation that is true, I know how to spell, for all values of the independent variable. So that's a bit of a mouthful. I'll let you guys get that down. And then I got some space here. We'll do a little quick example and non-example. An equation that's true for all values of the independent variable. All right, here's an example of an identity. I hope everybody would agree that this is always true. Would you guys agree that x plus x is equal to 2x? That's true no matter what number you put in for x. If x is 1, 1 plus 1, it's the same as 2 times 1. 5 plus 5 is the same as 2 plus 5. Would you guys agree? That's always true, right? That is an identity. A non-example would be, I'll pick a really simple equation. X plus 1 is equal to 3. That equation is not always true. It's only true for one specific value. And I have the space, I'll jot this in. It's only true when x is equal to 2. So there's an example of an equation that's an identity and one that's not an identity. So new term there. Let's pause. Anything you guys want to chat about? Identity is always true for any value of the variable. All right. So as I mentioned, you guys in the grade 11 course learn 3 identities. We'll get there in a second, but you actually pretty much already know 2 of them. The third one that's kind of new we'll introduce right now. And I should say too, if you're wondering why do we need these things called identities, it's really going to become more apparent for those of you guys who take some first year calculus courses. Not everybody will get there, but they can take really big complex trig equations and just make them simpler. Let's investigate another one. All right. I'm going to do a few of these with you. And for the first 4, we're going to use our exact values. We won't redraw our special triangles here. I'll just help you out. This will be some new notation for you guys here. You guys see the superscript on the sign? SIN, it just is just letters. It's meaningless. But that superscript 2, it's not squaring sine. It's squaring the sine of 0 degrees. So just for this one, can you guys just rewrite this one with me? This is saying the sine of 0 degrees, and then you square it, plus the cosine of 0 degrees, and then you square that. That's what that new notation means. It takes less writing to do it the first way, so that's just the notation we use. We're not squaring the letters SIN. We're squaring the sine of 0 degrees. Now you guys can use a calculator for this one, it's fine. But we probably can just do the exact value. Sine of 0 is 0. So 0 squared. Cosine of 0 is 1. And 0 squared is 0. 1 squared is 1. Would you guys agree that just equals to 1? It equals to 1. Let's do sine squared of 90 degrees plus cosine squared 90 degrees. So again, you can use your calculator for this one. You could use the unit circle too. 90 degrees is 0, 1. So the sine of 90. And maybe for this one too, just to get you used to this notation, I'll write this out one more time. This is not necessary. I'm just trying to reinforce this new notation. It's the first time you guys have seen this before. The sine of 90 is 1. So we get 1 squared. I wrote sine twice. You guys would copy down 2 plus 2 is 3 if that's what I wrote on the lesson sheet. Okay. Cosine of 90 is 0. And 1 squared plus 0 squared is 1. Well, we got 1 as well. Let's test out a few different angles. It seems like this is always going to give us 1. Let's test out another couple. Now, if you guys recall your special triangles, I'm going to actually use exact values here. The sine of 45 degrees was exactly 1 over root 2. Your calculator would give you like 0.7071, blah, blah, blah. It's okay if you did that. I'm going to leave things exact though. The cosine of 45 was also 1 over root 2. Guys, check this out. 1 squared is 1. The root of 2 squared is just 2. And then we also have another 1 over root 2 squared. That gives us 1 over 2. Last time I checked, what's a half plus a half? It's just 1. This also is equal to 1. This is fascinating. We're getting 1 no matter what angle we use. Let's do it again. Sine of 30. So I know that sine of 30 is a half. And I know that the cosine of 30, you could use a calculator and do decimals and you'll get the same result here, but I'm going to keep things exact. I know the cosine of 30 is exactly root 3 over 2 from our last unit. Does this work? I hope so. 1 half squared, that's 1 over 4. And then the root of 3 times the root of 3 is just 3. And then 2 squared is 4. And look, 1/4 plus 3/4 is equal to 1. They all equal to 1. To convince you even further, let's try a few more we don't have exact values for. Now you guys can just punch this all in on your calculator using brackets. You can do sine 81 and square it, and then you can do cosine 81 and square it. That's what I'm going to do. Sine 81, and then I'll square it, plus cosine 81, and I'll square it, equals to 1. This might seem like a bit of overkill, but let's do it some more, because maybe I cooked the books and it just works for these 5 values, or maybe angles between 0 and 90. Try 555 degrees. If I'm asking you to do it, I'll do it too. Sine 55, cosine 555. We're not going to spend all day plugging values in here. I'm just trying to convince you. Do you guys get 1 as well? Do you guys get 1? Nod and smile. Now, you can try it for the sine of 123 degrees and the cosine of 123 degrees. I think at this point is a little bit overkill. You're going to get 1. You can pick your favorite number, and you are going to get 1. I'm going to pick, I'll pick 34 because Austin Matthews not playing tonight. But if you do sine 34 degrees, cosine 34 degrees, it's going to give you 1. I think, have I convinced you guys? Do we need to do more calculator work? You guys convinced it's equal to 1? So what we have kind of shown, it appears that the following is true. that if you take the sine squared of an angle theta, and if you add the cosine squared of an angle theta, it appears you get 1 for all values of theta. It doesn't matter what you plug in. You guys kind of convinced? This identity is so important. It shows up in so many applications. It is so useful. We give it its own name, and we call it the Pythagorean identity. I still don't know how to say that word, Pythagorean. Now we don't call it the Pythagorean theorem. We call it the law of squares or something. But I know no other name than the Pythagorean identity for this one. So it's the first of 3 special identities we're looking at, the Pythagorean identity. It's always true. Now, in a second, I'll show you guys how we can kind of prove that. Right now, we've shown it works for a few different values. So hopefully you're convinced. So let's continue. All right. So here are the 3 basic identities you guys need to know in this course. We just saw the first one, the Pythagorean identity, sine squared theta. We're going to put them all in a little one-stop shop here. Plus cos squared theta is equal to 1. Now you'll notice I have some space here. That's because there's kind of like 2 other versions of this. You guys remember when you're doing Pythagorean theorem, normally we do a squared plus b squared equals c squared, right? But if you were back in, say, grade 9 math, and you were doing Pythagorean theorem and you were finding the leg of a triangle, you might do, to get a leg, you might do the hypotenuse squared minus 1 leg squared equals the other leg squared. It's not a different Pythagorean identity. It's the same one. It's just rearranged. Another version of this identity, we can say that 1 minus sine squared theta is equal to cos squared theta. That's not a different identity. It's just the same one rearranged. And in the same way, if you wanted like the other leg in a right angle triangle, you could just do subtract 1 leg from the hypotenuse, just the other one. So also 1 minus cosine squared theta is equal to sine squared theta. So I'm putting them all 3 there for later on for you guys. They are all the same identity, but just different versions can help you at different times. All right, here's the second one. I'm going to show you guys where this comes from in a second. The quotient identity says this, that the tangent of an angle theta is equal to the sine of an angle theta divided by the cosine of an angle theta. It's called the quotient identity because it involves dividing sine and cosine, a quotient. Can you guys humor me? The other one we beat to death for sure. But just to verify that that's true, can you guys take, I don't know, let's do 34 again. Can you guys do the tan of 34? And I get an answer. It'll be a weird decimal. That's fine. Tan of 34 about 0.6745 about. And then if on your calculators, you just do sine 34 degrees divided by cosine 34 degrees, you should get the exact same thing. Not close to it, like literally the exact same thing. Sine 34 divided by cosine 34. Yeah, exact same thing. That's the second identity you guys must know. I'll show you guys where that comes from in a second. And the third one, you guys actually already learned these in an earlier lesson, the reciprocal identities. So we had 3 of them. So if you recall, we had that cosecant theta was equal to 1 over sine theta. The reciprocal of cosine we called secant theta, 1 over cosine. And then we had one for tangent as well. The reciprocal of the tangent was called the cotangent ratio, and it was 1 over the tangent ratio. So that's not That's not new today. That's actually in your notes from a few days ago. But it's just one of the basic identities, the three that you're supposed to know in this course. Now, I would like you guys to add on a little bit here. If the tangent ratio is sine divided by cosine, and the cotangent is the flip of that, then we can also write the cotangent ratio as cosine of theta divided by sine theta. If you guys would write that down too, that will be helpful. Time-wise, we're doing fantastic. We're only 20 minutes in. This is great. Okay, so those are the three identities. We've kind of showed, hopefully, you're kind of convinced the first two are true. And the third ones we've seen before. Is there anything you guys want to chat about? All right, I would like to show you guys where those first two kind of come from. I'm not going to ask you to reproduce these proofs, but I think it's just helpful to know where these come from. And so when you guys all become math teachers, you guys can show your students too. I've drawn a right angle triangle there. Now, I didn't draw that. I did a Google image search, and I copied and pasted it over. So I stole this right angle triangle image from the internet. But I've got hypotenuse, opposite, adjacent labeled on there. I hope you guys would agree that if you take, because it's a right angle triangle, if you take the opposite side squared, I'll just use OPP, plus the adjacent side squared, that would be equal to the hypotenuse squared. Would you guys agree? Because that's just what the Pythagorean theorem says, right? I'm actually just going to, in brackets here, just make a little note that that's just the Pythagorean theorem. But check this out. We're going to take each of those three terms, and I'm going to use a different color here, and we're going to divide each of those three terms by the hypotenuse squared. And believe it or not, we have now proven the Pythagorean identity. Just from SOHCAHTOA. Look, opposite over hypotenuse. Is that just not the definition of sine? But we're squaring it. Opposite squared divided by hypotenuse squared. That is just the definition of sine squared theta. Sine is opposite over hypotenuse. Adjacent over hypotenuse. That's cosine. But we're squaring those. So cosine squared theta. And then finally, anything divided by itself is just equal to 1. So nifty proof of the Pythagorean theorem using SOHCAHTOA. Now, that's for angles between 0 and 90. We can show it's true for all, but I think that's just enough for to convince you guys it works. So that's pretty neat. All right. You guys okay with what we did there? I mean, honestly, if I were you guys and I said prove the Pythagorean identity and gave you guys 3 marks for it, I'd be kind of happy. But I don't generally ask you guys to reproduce proofs. How can we prove the quotient identity? So I want you guys to do this along with me here. I might be a little naughty and work left to right, more than 1 equal sign per line. But if you guys don't tell Miss Plattner, then Miss Plattner used to teach here. She's my math mom. All right, we're going to start proving the quotient identity by looking at sine theta over cosine theta. Now, it's the sine of theta, just going back to SOHCAHTOA, is opposite divided by hypotenuse. And on the bottom, the cosine of an angle is adjacent divided by hypotenuse. Now, in this math course, we should be okay dividing 2 fractions. We've actually divided rational expressions earlier in the year. But recall, when you divide 2 fractions, you change it to multiplication, and you flip what you're dividing by. So if I take opposite over hypotenuse times, and I flip the bottom, that's hypotenuse divided by adjacent. That's just that's just dividing fractions. But look, you have a factor of the hypotenuse on the top and the bottom, and those divide to 1. They kind of cancel out. And what you're left with is opposite over adjacent, which is the very definition of the tangent of angle theta. So we've kind of proved that one as well. All right. Anything you guys want to chat about? So those are the 3 basic ones. Those you just got to know. These, what we jotted down up here, you just got to have in the toolbox ready to whip out at any time, okay? But luckily, you've seen these ones before. This one's not too hard to remember. This one's not too hard to remember. But what we're going to do next is, and what the expectation for you guys in this course is, you guys are expected to know these 3 basic ones and use these basic ones to prove some slightly more complicated identities. So that's what we're going to move next. Here we go. Hold on to your butts. We're going to prove this wild-looking identity. Sine theta times cosine theta times tan theta times cosecant theta times secant theta times tan theta is equal to 1. Now, I want to be very clear. It is not enough just to plug in a couple of angles and show that it's true. That only shows it's true for 1 or 2 different angles. To prove an identity, you have to prove it's true for all angles. So, normally, or one strategy for proving identity is taking one side that looks kind of more complicated than the other, and trying to simplify it down. Now, this might be a bit of a stretch, but would you guys say the left-hand side looks just a teensy more complicated than the right side? I would argue that that is true. So we're going to start with the left-hand side here, and we're going to see if we can manipulate that left-hand side and make it equal to 1. One strategy is when you guys see cosecant. This should be cotangent. I just recognized that for you people at home. I'll fix it when I post the lesson sheet later. One strategy, when you guys see cosecant, when you guys see secant, when you guys see cotangent, you guys should maybe think, okay, well, maybe I can use my reciprocal ratios here. So the left-hand side, if we do that, becomes this. We have sine theta, cosine theta, tan theta. But cosecant is just the reciprocal of sine. And secant is just the reciprocal of cosine. And cotangent is just the reciprocal of tan. And because I have the space here, just in brackets, I'm just going to put in brackets here reciprocals. I just use my reciprocal identities there. And then we're basically done. What's sine theta times 1 over sine theta? Well, like anything times its reciprocal just gives you 1. It's like 2 times a half or 4 times 1/4. So I'm just going to basically crisscross applesauce all these guys out. They all divide to 1. And literally, we're done. We have shown that that complex left-hand side is just equal to 1. And when we were done proving an identity, we've shown the left-hand side equals the right-hand side. We just kind of finish it off by saying, okay, that equals the right-hand side, little check mark. We've proven our first identity together. Very cool. Left side equals right side. We use the reciprocal ratios there. Let's do another one, and then maybe take some questions, and I can suggest some strategies for proving more complex identities. So here's another one. Oh boy. We're going to prove that 1 minus cos squared theta is equal to sine theta times cosine theta times the tan of theta. Now, for me, I look at either side there and I say, you know what? To me, those two sides are about comparable in how complex they are. It's okay when you're proving identity to actually work with separate sides at the same time. Here's what I mean by that. Let's look at the left-hand side. And I have a lot of space here, so I might just rewrite the left-hand side down below. The left-hand side is 1 minus cos squared theta. Did we not just kind of learn an identity that helps take that and maybe simplify it a bit? 1 minus cos squared theta, that's just equal to sine squared theta, is it not? That makes it a bit more simple. So that left-hand side, we can just rewrite as sine squared theta. I wonder if we can take the right-hand side and manipulate that right-hand side to make it look like sine squared theta. Does anybody have any ideas? So we have three basic identities to work with. We've got the Pythagorean identity, and this right-hand side doesn't have any squares in it, so I don't think that'll help us. We have the quotient identity, the tan theta is sine over cosine, and we have our reciprocal identities. Do you guys see any reciprocal identities or reciprocal ratios here? Sine, cos, tan? There's no reciprocals in here, right? You have an idea, Paige? Well, we use that on the left one. On the right-hand side, if you don't see a squared, it's kind of hard to use that one. But we did use it on the left. What do you think?
Maybe the quotient identity?
The quotient one? Yeah, guys, check this out. When you guys see tangent, one strategy for proving identity is to rewrite tangent as sine over cosine. Tangent is sine theta over cosine theta. And this isn't necessary, but just for our note, I'm just going to, in brackets, write quotient. We use the quotient identity there. Aha! Look at this. Does not cosine theta divided by cosine theta equal to 1? Scratch them off. What are we left with? Sine theta times sine theta, that's just sine theta squared. That's just sine squared theta. It's exactly what we showed the left-hand side was equal to. We've shown the right side is equal to the left side. We've proven a more complex identity we use Pythagorean identity there, and we use the quotient identity as well. Very cool. We've done 2. Anything you guys want to chat about so far? Mackenzie, was that you just stretching your hand? Okay. Where'd the tan go? We replace tan with what it's equal to. The tan of theta is equal to sine theta divided by cosine theta. Okay? Yes. What did I? The rest of what ones? What would I replace sine theta with? I could, but I mean, it doesn't help my ultimate goal. The goal is to show that this identity is true. So replacing things with O over H might not be helpful here.
So how do you know to do that one?
How do I know to do that one? So this brings me to my next tip. Now, before I say that, generally, the question of how do you know to do that here, it comes from experience and doing more practice. And we've just done a couple, but here's 2 big tips for you guys. I think they're down here, yes. So the first big tip I have for you, which is what we did in example 2. In example 2, if you guys see a tan or a cotangent or a cosecant or a secant, rewrite them in terms of cosine and sine. So in example 2 there, on the right side, we had a tan theta. See you later, tan. I'm going to make you into sine over cosine. When everything's in terms of sine and cosine, you can sometimes use some algebra to simplify a bit. The second thing to look for is if you notice a ratio is squared, And I might actually make a little, I'm going to say example 2 on the right hand, on the right hand side. If you notice a ratio is squared, that's a big clue. If you see a squared, then the Pythagorean identity might be useful to you, just like in example 2 on the left-hand side. But yeah, Jesse, your question is a very good one. How do you know to do that? It comes from experience. I've been doing this a long time, so obviously I have a lot of experience. You guys are just starting to prove some identities today, but those 2 ideas will help you. Replace everything in terms of sine and cosine. If you see something squared, maybe you can make use of the Pythagorean identity. All right, let's try another one. Oh boy, what have I gotten you guys into? That is a crazy looking trigonometric identity. I wouldn't even know where to start with the left-hand side, right-hand side.
We do not have that.
You don't have that?
In our package, no.
Nobody has that?
Let's go. Yeah.
Okay, I have it.
No.
Okay, YouTube, we're just kind of trouble on me. All right, guys, listen up. Another strategy for proving identity. Sometimes you don't necessarily have to work with the identity you're given. Sometimes you can actually rewrite the identity you're given in a way that kind of makes it easier to prove. Now, what I mean by that is, this is kind of like a proportion, right? And we can cross multiply, like we're not actually solving a proportion here, but I can multiply this sine theta over here and this 1 plus cosine theta over here. Follow along with me as we do that, and I hope that you guys are convinced it's going to make things a little bit more manageable. So I'm going to, I don't think it's worth rewriting. I'm going to cross multiply here to maybe make this a bit simpler. Cross multiply. All right. What does that give us? Well, we have sine theta times sine theta, and that will give us on the left-hand side sine squared theta. And on the right-hand side, I'll have 1 minus cosine theta times 1 plus cosine theta. Now, I know many of you guys don't like working with rational expressions. We just got rid of all the fractions. I would argue that looks like more manageable to work with. That's just my opinion, though, but I think it is. That left-hand side is looking pretty simplified. I don't think I can do anything with that left-hand side. The right-hand side, though, I think I could do some stuff. So let's take the right-hand side. Let's begin. The right-hand side, I'll rewrite it. It's 1 minus cosine theta. It's 1 plus cosine theta. Now that looks like a binomial times another binomial. And you guys know how to multiply 2 binomials together. You can use FOIL or whatever you guys call it, double rainbows. FOIL, first outside, inside, last. But yeah, let's try just multiplying those 2 binomials together, and we'll see what kind of falls out. 1 times 1 is 1. Last time I checked. 1 times cosine theta is just cosine theta. Minus cosine theta times 1 is minus cosine theta. And then minus cosine times or plus cosine, that's minus cosine squared theta. Now, where did this get us? Guys, what's cosine theta minus cosine theta? 0. They wipe out, right? So we're left with 1 minus cos squared theta. I sure wish there was an identity that could turn this into, Mackenzie, what were you going to say? That is literally equal to sine squared theta. Yeah, that's the Pythagorean identity. Equals the left-hand side, yay us.
Wait, how'd you just change the sign?
Because, zoom, 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 because the Pythagorean identity, 1 minus cos squared theta is equal to sine squared theta. They are equal. They are equal. It's an identity. It's always true. 1 minus cosine squared is equal to sine squared. We did it. That's probably the hardest identity we're ever going to prove together. Yeah. Who created them? I don't know. To answer those kind of questions, I can't really do this stuff until I can't really answer those questions until you guys are in like a first year university level course. But that's the thing. So you guys are taking this course to prep you for grade 12 functions, which preps you for calculus, which preps you for university math. Eventually down the road, you will need these skills to do those high level courses. It's hard to explain the whys because you guys aren't going to get there till like 2 more years. You just have to trust that these skills are necessary. This is the time in your math careers where you're introduced to them. That's the best answer I can give you. All right, we're going to do one more together, and then I think that's a kind of a broad variety of identities for you guys to prove. Now, I'm going to do the left-hand one with you guys, and then you guys are going to do the right-hand one using a very similar method. All right, here we go. Now, you guys see the squared here, tan squared and secant squared? You might think, well, maybe I can use the Pythagorean identity, but does the Pythagorean identity involve tan or secant? No, just sine and cosine. So maybe we'll put a pin in that. Another strategy is when you guys see tan, you guys see secant, rewrite them in terms of sine and cosine. We know that tan, I'm going to start with my left-hand side here. Tan is sine over cosine. I'm going to replace tan squared with sine squared theta over cosine squared theta. Because tan theta is equal to sine theta over cosine theta, plus 1. Yeah, that's the left-hand side, right? Now, do you guys remember, you guys might maybe have some PTSD and block this from your minds, but remember when I taught you guys how to add 2 rational expressions together, 2 fractions involving algebra together? We did learn that. I'm going to do it with you guys here, but it's not so bad, actually. We need a common denominator here. We don't got to work too hard. Can you guys do this with me? We can write 1 as cosine squared theta over cosine squared theta. Why are we doing that? Because we want to add these terms together, and we need a common denominator. But now that we did that, we can just add these 2 expressions together to get this. We get sine squared theta plus cosine squared theta. And on the bottom, our common denominator of cosine squared theta. Now, how the heck did that help us? Look at the top. Look at the top. Sine squared theta plus cosine squared theta. What's that equal to?
1.
It's equal to 1. That is equal to 1 over cosine squared theta, which is secant, right? Which is the right-hand side. We got it. I'm going to zoom out a bit to keep this all in. This is equal to secant squared theta, which is equal to the right side. We did it. Now, that was a lot of steps. I might add just quickly in brackets here because I have a bit of space. We use the quotient identity there. And then we use the Pythagorean identity here, just for when you're going back and studying. It had a few steps, but really everything was manageable. We rewrote tan as sine over cosine. We added those 2 expressions together by writing 1 as just cosine squared theta over itself. And then we used the fact that sine squared and cosine squared was equal to 1. We did it. And I guess at the end, we used the reciprocal ratio. That one had everything. Fantastic. You guys took that like champs. That was using reciprocals. Now, I'd like you guys to try the one on the right using the exact same strategy. I'm even going to help you guys out to get started. If you take the left-hand side, you can rewrite that as 1 plus, if tan is sine over cosine, we talked about this earlier, cotangent is cosine over sine. Can you guys use the exact same process to try and show that left-hand side is equal to cosecant squared theta? You can do it. I'm going to pause the video and start up again in a second once you guys have had a chance to try it home. Zoom. So if you're watching at home, I'm just playing catch up with proving this you try it one. We're using the same strategy as the left-hand problem. But yeah, we get this idea, and whenever you guys see sine squared plus cosine squared, you can immediately just replace the whole bit with 1. 1 over sine squared theta, which is cosecant squared theta, which is the right-hand side. Yep. Equals the right-hand side, little check mark. All right, so I'm going to end the video here and then just talk about the practice you guys are doing.